So the firm's going to face prices for inputs. I'm going to call them W1 and W2 for corresponding to X1 and X2. And so those are the prices it has to face. Now, this is the cost minimization problem. It wants to minimize its total costs of purchasing the inputs. So you can see this. We have we're going to choose X1 and X2. Those are the inputs. They might be things like capital and labor, for example. We're going to choose those inputs so as to minimize total expenditures, the total cost the firm faces, subject to a constraint. And the constraint is that the firm is going to choose its inputs so that it's able to produce a quantity Y. So that's the idea. So what problem does this remind you of? It's a lot like the consumer's expenditure minimization problem. The only difference really is that we have a U here instead of an F, and maybe a U on the other side. We could be minimizing total expenditures subject to delivering a given level of utility in the consumer's expenditure minimization problem. But otherwise, the problem is very similar. And you'll see it has the way we're going to solve it is going to be similar, and a lot of the tricks that work for utility are going to work here as well. Okay. All right. So with that cost minimization problem, let me go ahead and write out an example for you, and it'll be an example that involves a Cobb-Douglas reduction function. So I'm going to write out this problem. The only thing I'm going to do really differently is to assume that we know what F is and assume that it's a Cobb-Douglas function. So let me go ahead and write down that problem for you by way of example. Okay, so what I'm going to do here is assume exactly that that the production function f of x1, x2 is equal to a times x1 to the alpha 1, x2 to the alpha 2. And so that's the production function. That should be familiar from our last couple lectures. And then the problem, I'm just going to copy this problem up here. The cost minimization problem is to minimize by choice of x1 and x2 the total cost, which is w1 times x1. So these are the costs of purchasing the first input, plus w2 times x2, cost of purchasing the second. And I hope it's obvious how this extends to any number of inputs. If we have n inputs, we just keep going with the sum. And we have, in the Cobb-Douglas case, we could add x1, x2, x3, and so on. Okay, so we're going to minimize expenditures. We're going to do this subject to the constraint that a, x1 alpha 1, x2 alpha 2 is equal to some level of output y. And I'm going to note in passing that so the firm's going to take w as given, and for this part of the problem, it's going to take y as given. So it's thinking about, if I have to produce y, what's the cheapest way to do it? And so the solution to this is going to yield a function which will depend, we'll call it the cost function, which will depend on the amount of y the firm has to produce and the input prices w it faces. So notice what price doesn't show up in here. There's no price for the output. The firm cares about that, of course. It cares about its revenues as well as its costs. But for this piece of the firm's problem, they just take y as given, whether they're making money on it or not. So they have to produce y. It doesn't matter what the price of y is. They only care about for this stage, what's relevant are the prices of the inputs, w1 and w2. Is that statement of the problem clear? Okay, I'm going to go ahead and sort of solve this problem, or characterize the solution at least. So let me do that by noticing that I've got an equality constraint here. That's the assumption we've got. So I'm going to tackle this problem by formulating this as a Lagrangian and getting some first order conditions and proceeding in the same way we've done for expenditure minimization problems with the consumer before. So I want to rewrite this thing as a Lagrangian. I'll be minimizing with respect to x1 and x2. My new objective function will be w1 x1 plus w2 x2 plus a multiplier mu times y minus a x1 alpha 1 x2 alpha 2, and that's the formulation of the problem that now involves an unconstrained minimization problem. Okay. Everyone happy with that? No mistakes yet? Okay. All right, so let's go ahead and get our first order conditions. The first one is going to be with respect to x1. So where does that show up? What do we get for this? The partial derivative of this expression with respect to x1. So I see it shows up in two places. The first place is really simple. There's a w1 that comes from this, and it's linear, so the x1 disappears. The other place is here. So what else do we have? Yeah, so I have a minus mu, this is the Greek letter mu, little mu, times, and what do we got here? Good. Nice. Okay, good. And at the optimum, of course, is going to be equal to 0, so I'm just going to write it this way. Okay. We're going to get something awfully similar for x2. I'll just write this one down because we can rely on symmetry here to say what this is. We don't even need to take a derivative. This has to be w2 equal to mu alpha 2, a, x1 alpha 1, x2 alpha 2 minus 1. So those are our two first order conditions. The next thing I want to do with these is do my trick of dividing one of these by the other. And so let me go ahead and do that. So if I divide this expression by this expression on both sides, then what I'll get is w1 over w2 from the left-hand side of this expression. On the question, or?
Don't you have to take the first order condition of the mu expression as well?
Yeah. So the complete set of first order conditions from this will include a derivative with respect to mu. Just give us back the same constraints. I'm not bothering to write here. But I mean, this still will characterize the optimal solution for sure. That's important. Let me come back to that. Okay. So we get w1 over w2 on the left-hand side. From this side, you can see a bunch of stuff is going to cancel out. So the mu is going to cancel out. The a is going to cancel out. Alpha 1 of these x1s are going to cancel out. So let's have a minus 1 x1 still. And alpha 2 of these are going to cancel out. So I'm going to wind up with an expression alpha 1 over alpha 2 times x2 over x1. And so that's an expression that emerges from these two first order conditions. And just a reminder, there's a picture that goes along with this. Optimality condition. Anyone know what it is? What's this? We have a name for this thing. This is the marginal rate of technical substitution. And that in turn is the slope of an isoquant that involves production y. So the slope here is alpha 1 over alpha 2, x2 over x1. And of course, it's also and what this is telling us is we want to find a slope here, so that the slope at this point, the marginal, I actually read this up here, sorry, let me do this. At this point, the slope is alpha 1 over alpha 2, x2 over x1. The slope of this line is just w1 over w2. So what this equation is telling us is we want to find the point on the isoquant where the slope is equal to this ratio of prices. All right, yes? The slope is minus, I'm not sure I'm going to count as a mistake. Yeah, the slope is absolute. I mean, I'm going to, if I give extra credit for that, then we're going to have a degenerate grading outcome. So yeah, whenever I talk about slope in a space like this, we should be thinking in terms of absolute value. Okay. Thanks for catching that. Okay. All right, yeah, so this is telling us where to find the optimal point, and so you can see it's going to wind up telling us that we should get a point x1 star and x2 star at the optimum. Okay. Yes. The straight line is the line. Okay, good. Okay, I'm glad you asked. The straight line is the line that has a slope which is equal to this ratio of prices, and which is tangent to the isoquant that produces a total level of output y. Okay, so each of these isoquants, there will be a different isoquant for each possible level of output, and we're going to choose the one which is this. Remember, the firm's taking this as given. So if Tesla Motors is supposed to produce 20,000 vehicles, we'll set y equal to 20,000, then we'll figure out the cheapest way to do it, and that'll depend on the price of inputs, batteries and engineers or something. Okay. So here's that same picture. So if we take y equal to 4 for a production function with alpha 1 equal to 1/3 and alpha 2 equal to 2/3, here's the picture I reproduced there. Okay, so we've got this cost minimization problem here. What have I done? Yeah, so we've got the cost minimization problem here. You can see that graphically, these two, we actually haven't even used this to pin down y graphically. And having pinned down this isoquant with this constraint, and then use these two first order conditions, we figure out what the optimal level of x1 and x2 are. So this optimal level of x1 and x2 are what we'll call the input demands. So this slide describes those. So this graph, or this equation, along with this constraint, allow us to work out what the optimal amount of the inputs the firm will use are. So we can figure out from these two boxed expressions how much x1 and how much x2 a cost minimizing firm will employ. All right, so the name of those are input demands or factor demands. We'll use those interchangeably. Okay, so let's go ahead and continue our example here. And what I want to do next is just work through, just continue this example to solve for the firm's factor demands, to solve for these functions x1 and x2 as a function of output y and of prices w, input prices w. So that's the next thing we'll want to do on the board. Okay, so as I said already, the starting place for us is going to involve these two box expressions on the board. So first of all, this thing on the bottom, which is a statement that the marginal rate of technical substitution has to be equal to the ratio of prices. That's going to show up all the time. And then second of all, this constraint, which is a statement that total output has to be equal to y, has to be equal to the quantity y that the firm is tasked with producing. Okay, so from here it's really just algebra. So what I want to do is rearrange things, and I rearrange this expression involving the marginal rate of technical substitution, and substitute it into the constraint, and then solve for x1 and x2. So from maybe I should give these names. Let's call this dagger, and let's call this star. So from star, that's the requirement that the marginal rate of technical substitution be equal to the ratio of prices. We're just going to multiply this, I'm going to move this stuff around and write x1 in terms of x2. So I'll have x1 in this case equal to alpha 1 over alpha 2 times w2 over w1 all times x2. And you might note in passing that this is an expression for the isoquants if I write it this way. If I put x1 on the vertical axis, what I've done here is written an expression for the isoquant. All right, so that's, I'm sorry, that was a mistake, excuse me, not for the isoquant. So there's a bunch of isoquants here. What this is an expression for is what the so-called isocline would be. So if we have an isoquant here, and same slope here, because we face the same prices, if we pick out a level of x2, this tells us how much x1 to use, and that traces out the optimal mix of x1 and x2 given prices that the firm faces. But not, you'll notice, given output. This doesn't depend on y. So this is an expression for the so-called isocline that tells us if we're going to use some quantity x2, how much x1 should we use if we're going to minimize costs. Okay, so anyway, so we've rewritten the condition that the marginal rate of technical substitution is equal to the ratio of prices in this way. Now I just want to substitute this expression into the constraint. So we're going to substitute into cross. That's going to give us a times, here I'm replacing x1. So alpha 1 over alpha 2, w2 over w1, x2, all raised to the alpha 1 times x2 to the alpha 2 is going to have to be equal to y. So what I've done now is eliminated x1. The firm is going to take the parameters of the technology, a, the alphas, the prices, all is given, and so now we just need to solve for x2. It'll wind up looking like a function of the stuff in this expression. So we'll wind up x2 as a function of the alphas, the w's, a, and y. Okay, so now from here it's just algebra. So we'll have, I'm going to rearrange this a little bit. This implies that y is equal to a times alpha 1 over alpha 2. Oh, that's a mistake. You guys didn't catch it either. Okay. W2 over W1. W2 over W1. I'm going to factor, so this will all be raised to the alpha 1. I'm going to factor out this x2. So I'll have x2 to the alpha 1 plus alpha 2. And that's my new expression. So I just factored out the x2 here. continuing, what I want to do now is divide all this stuff to the left-hand side, and then I'm going to take the 1 over alpha 1 plus alpha 2 tooth root. Okay? So that'll give me x2 equal to this expression, y over, I'll do it this way, y over a times alpha 1 over alpha 2, w2 over w1. All raised to the alpha 1. So I'm taking my notes. Okay, let's see. So where was I? I think I'm done there. So this thing all now divided by 1 over alpha 1 plus alpha 2. All right, and maybe I'll rewrite this a little bit to make it just a little bit prettier. I'm going to do that by just dividing, putting this thing up here. So we'll get x2 equal to y over a, all times alpha 2 over alpha 1, w1 over w2, all raised to the alpha 1. This whole thing raised to the 1 over alpha 1 plus alpha 2. So I think I got this right. This would be a good time to check carefully, make sure I didn't make mistakes, because my notes are wrong, so I'm doing this one off the cuff. Okay, now by symmetry, so what is this? This is the input demand for x1. It gives it, for x2. So x2 we express as a function of total output we need to produce, prices, and then just a bunch of technological parameters. So this is the input demand for x2. Let's get the same thing for x1, but here let's use symmetry. So x1 by symmetry will give us what? Still have y over a. I agree. What else? Yeah, so let's go through and switch around the subscript. We'll have alpha 1 over alpha 2. We'll have w2 over w1, all raised to the alpha 2. Good. And then does this thing change? No. This whole thing now raised to the 1 over alpha 1 plus alpha 2. Okay, so these two things give us what we're after, namely input or factor demands for the firm, for the cost minimizing firm. Okay. All right, that's excellent. Let's take a look at these things for a moment. And just give a little bit of thought to how the input demands behave as we vary output and prices. Okay, so here, let me first ask you a trick question. What happens if we double all the input prices? Now, we can see from the expression it's not a very hard trick question. If you double all the input prices, the only place these things appear is in a ratio like this, like W2 over W1, W1 over W2. So if we double them both, it's not going to have any effect on input demands. So why is that? We just doubled prices. Why is the firm not responding by changing its demand for inputs? Yes. Well, so maybe, right? So the answer is you're assuming the answer when you say that, I think, which is okay. But yeah.
Because their output is fixed?
Because the output is fixed. So I mean, for the firm to continue to survive, they would need to be able to pass the cost on to consumers, perhaps. But in this case, the problem they're solving is to produce Y, no matter what. It doesn't matter whether they're making money or losing money. They're just trying to figure out the cheapest way to do it. And if the prices of all their inputs double, well, their costs are going to increase, and they just need, to produce Y, they just need to lump it. Okay. So that was the trick question. Here's a non-trick question. What happens? We've got some other parameters to play with here. What happens to input demands if this technological parameter A increases? We used this before to talk about the technology that the firm is using. So if A increases, how does that affect input demand? Yes.
The demand will go down.
It'll go down. It'll go down exactly in proportion to Y, right? So if A doubles, then we can produce twice as much A with the same number of inputs, or we can produce the old value of Y with fewer inputs. That's good. Okay. What about so what happens if we increase Y? What happens to input demands then? How should we graph? Let's think about graphing x1 as a function of Y, holding prices and the other things fixed.